I'm Charn Gregory, and this is my lab number 5, magnetic molasses lab. So the main point of this lab is to demonstrate the effect of Faraday's law and the effect it has on a magnet being dropped through an aluminum tube. So we use a physical aluminum tube, and then we also use a separate glow script model to represent our physical aluminum tube and magnet situation. In order to do this lab, we need to know Faraday's law, how the change in the flux is EMF is equal to the change in flux, and then Lenz's law just tells us that the EMF is going to try to counteract what the change in flux is, so it's going to be in the opposite direction. Ohm's law, we need to know that EMF is equal to current times resistance, and then we need to know how to find magnetic flux and magnetic force. So quickly summarize the results. We got 1.584 seconds for the magnet to fall. And then this is through our physical experiments. Through our glow script code, we got about 30.3 seconds, which I forgot to write down. So in this lab, we basically find the north pole of a magnet. We drop the magnet and record ourselves doing it. And then we use the timestamps and we try to find the time it took for the magnet to fall. And then we repeat that 5 times and we average our times in order to find average time of 1.54 seconds. So our system's magnet in the tube, surroundings the Earth, and initially our magnet is at rest on top of the cylinder. It is the cylinder is facing like vertically, and then magnet's mass is 0.25 kilograms. The tube is 0.47 meters, radius is 0.02 meters, and the magnetic dipole moment from we found from lab 3 is 5.15. So these are just the times we got for each trial. And then, yeah, so basically Faraday's law means that as a magnet falls, it changes the flux experienced by certain points of the tube, which means that nature will try to counteract this change in flux by inducing currents in the opposite direction. And these currents will create magnetic forces and magnetic fields that oppose the change in flux through the magnet, and then they oppose the motion of the magnet, which results in the magnet falling down slower and having a smaller magnitude of acceleration. So this is our glow script code. The slide comes before the first slide, but this is our results for the properties of our tube and our magnet. And then we also calculate the magnetic flux using the formula integral of magnetic field times area. And then we just integrate it out, and then we get a formula that's represented in this calculate deflux method. And then this is the second part, which just models the multiple rings, and then it actually does the simulation, keeping track of time and keeping track of velocity and the location of the magnet as it falls down the tube. So to analyze the results, it's not pictured in this picture because this is at the end of our simulation, but while the magnet is in the middle of our tube, there's a red current below the blue current, and that acts as our induced current. So the red current is counterclockwise because it acts against the motion of the velocity of the magnet, and then the blue current is clockwise. If the magnets were flipped, then the induced current would provide a magnetic field in the opposite direction, facing downwards. But should remain the same. So in simulation fall time, we got 3.2 seconds, which is about double of what we got in our physical experiments. As we can see, the acceleration is mostly the same, is mostly 0 for the movement of the magnet, which means that our induced magnetic force is roughly equal in magnitude to the gravitational force experienced by the magnet. So the possible source of error is human error when we were using a stopwatch or looking through timestamps to find the time it took for the magnet to fall through. And then also the aluminum could also be inconsistent in its density, which affects the movement of currents. And we also relying on a magnetic dipole moment from lab 3. So what if our resistivity was very low due to Ohm's law, and this current would be so large in magnitude, it would create a magnetic field enough to do more than just counteracting gravity, and the magnet might actually go to almost zero in speed. So the magnet might almost start floating in the middle. If holes were cut, there would be less surface area for current to flow through, which means that the magnet would basically fall down faster because the opposing magnetic force would be reduced in magnitude.